What if our matrix A is non-diagonal, if it's not nilpotent, and if it's not satisfy the property of the item 3 in previous slide? So in this case, we can again look at the matrix A minus Ri to the power m. But now we don't know if it's 0, but we can apply this to some vector u and make it 0. And this vector u is called generalized eigenvector. This is generalized eigenvector because for m equals 1 this is just usual eigenvector. So what if we can find this vector u and this number r and this power m such that this one is 0? What can we do in this case? Can we find e to the at using this? In fact, no. But we can find e to the at applied to the vector u. And using the same idea as before, we can do this. So this is a minus rit applied to the vector u. And this one again we use the definition of matrix exponent. So this is just I applied to the vector u, the matrix applied to the vector u t plus the matrix squared applied to the vector ut squared over 2 factorial plus and so on. And this sum will stop at the term m minus 1 because the m's terms is 0, right? So a minus ri to the m minus 1 applied to the vector u is non-zero, and this is the last term of this sum. So we can calculate all of this and can find e to the at applied to the vector u. What this gives us? So if, let's say, R1 is eigenvector of A of multiplicity 1, then we can find there is u1. Sorry, it's not eigenvector, it's eigenvalue. There is eigenvector u1 such that A minus R1 I applied to the vector u1 is 0. And so we can find one eigenvector, and from this we can find easily e to the at u1, right? So if, say, another eigenvalue say of another multiplicity, let's say 2, then we can find exactly 2 generalized eigenvectors which are linearly independent, and find, so let's say u2 and u3, and using this formula above we can find e to the at applied to u2 and e to the at applied to u3. In fact, if R2 is eigenvector of multiplicity 2, then what we use, that A minus R2I squared, how we find the generalized eigenvectors u2 and u3, is 0 from this formula. So this is u2 and u3. Okay, and similarly, if if Rm is eigenvector of A of multiplicity m, then from A minus Rm I to the power m u is 0, we can find exactly m linearly independent generalized eigenvectors. So for n times n matrix A, we can find exactly n eigenvalues, right? And n linearly independent generalized eigenvectors. Some of them may be just simple eigenvectors. So let's say we denote the set of eigenvectors u1 and so on un, and so we can find EAT u1 and so on EAT un, the fundamental solution set of the system x prime is AX. Why it's a fundamental solution set? Because each of them is a solution, right? Each of them is a solution. Each of EAT UG is solution of the system, because we've chosen this e to the AT, so that e to the AT C is solution, right? So for any vector C, so in particular for any UG. And since these things u1 and un are linearly independent, these are also linearly independent. Since are linearly independent. So we can construct, using this set, we can construct fundamental solution set, so we can construct solution, general solution for the system, and we can construct the fundamental matrix. So the fundamental matrix x of t can be constructed using, so this is a matrix which columns are these things here. Okay, so we have fundamental matrix, and in fact e to the AT also fundamental matrix, right? E to the AT is also a fundamental matrix. So how we can find e to the AT, and what is different between x of t and e to the AT? The difference is just in the constant vector. So x of t, the solution, is e to the AT applied to, let's say, C1, and x of t also fundamental matrix, so this is solution is x applied to maybe some another vector C2. So how we can find this e to the AT? We can take t equals 0, and we will get that C1, vector C1 is x of 0 times vector C2. Now if we multiply both sides by x of 0 inverse, we get that C2 is x of 0 inverse C1. If we substitute it here, we obtain e to the at C1 is x of t x of 0 inverse C1. And C1 can be arbitrary constant vector, so it means that these two matrices are the same. So e to the at is equal to x to the t x of 0 inverse. So this is the idea how we can find the matrix exponent using fundamental matrix for solution of the system. So this is connection of e to the at with fundamental matrix of x prime x ax. Okay, let's have a look at an example where we will use this formula. Let's say we want to find e to the at for this particular matrix A. And the first step that we do, we find the eigenvalues. So we solve this equation. Let me write the precise expression for this determinant. This is minus r minus 1 squared r minus 3. And so what do we have? This one must be equal to 0. We have that r is 1 is eigenvector of multiplicity 2, and r is 3 is eigenvector of multiplicity 1. Eigenvalue of multiplicity 2, eigenvalue of multiplicity 2, and this one is eigenvalue of multiplicity 1. We take multiplicity from the powers here. This is 2, so multiplicity 2. This is power 1, so multiplicity is 1. Okay, so what can we do to find two eigenvectors for these two eigenvalues? So we look at the matrix squared applied to U. And this one, in fact, let me just write the matrix. And we need to find U. So let's say x, y, z is 0. So this one gives us x plus 2y is 0, so x is minus 2y, and z can be any, right? So we can take z to be s, one parameter, and say y is another parameter. So vector u is x is minus 2t, y is t, y is just t, and z is s. So this is s times 0, 0, 1 plus t times minus 2, 1, 0. And these two can be taken as these two linearly independent eigenvectors. These are generalized eigenvectors. Okay. And what we have to do now, we have to find also eigenvector for the third eigenvalue. So for R3 is 3, we have the matrix is, okay, this is minus 2, 0, 0. 1, 1, 0, and 0, 1, minus 2. sorry, it should be 0 here. 3 minus 3 is 0, minus 2 and minus 2, yes. So this one applied to, let's say, x, y, z is 0. So we have that x is 0, right? And we have that y minus 2z is 0, so y is 2z. So we can take z to be s, and then u will be 0 to s, s. So this is s 0 to 1. So this is our eigenvector, just usual eigenvector u3. And now we need to find e to the at u1, e to the at u2, e to the at u3. So let's do this. E to the at u1, this is, so the eigen value for u1, it was just 1, so this will be e to the t, here the eigenvalue is, and here we have I u1 plus I minus a minus I u1 t, and for second power we already get 0, right? Because this u1 is so that the second power is 0. So we stop here. And so this is e to the t, and the identity applied to u1, we just get u1 plus, and a minus identity will be just 0, 0, 0, 1, 2, 0, and 0, 1, 0. So e to the t, and what was u1? This is 0, 0, 1 plus this thing applied to 0, 0, 1 t, e to the t, and here we get 0, 0, 1 plus, what is this vector? 0, the first component 0, then again 0, then again 0, just nothing. So we get just 0, 0 e to the t. Okay, let's find the same for the second vector. This is e to the t I u2 plus a minus I u2 multiplied by t, and so this is e to the t, and what was u2? It was minus 2, 1, 0, plus this matrix is 0, 0, 0, 1, 2, 0, 0, 1, 0, applied to minus 2, 1, 0, multiplied by t. So this is e to the t minus 2, 1, 0 plus 0, and here we get minus 2 plus 2, again 0, and here we get 1 t. So the answer is minus 2 plus 0 is minus 2 e to the t, and now e to the t here, because we have 0, only t, and also e to the t. So in this case the answer is here, and e to the at u3, for u3 we know that the first power is 0, so we just stop at e to the eigenvalue was 3 t, and the eigenvector u3 was 0 to 1, so the third component of our matrix is this one. So now we construct x of t, the fundamental solution. In fact, what we did just now, we just solved the system. So we have solved the system x prime is ax. And now we need, from the solution, we need to get e to the at. So, and we write the solution in the form of fundamental matrix. So what was the first column of the fundamental matrix is this one. The first column, 0, 0, e to the t. 0, 0, e to the t. The second column will be this one, minus 2, e to the t, e to the t, t, e to the t. And the third column will be this one. So this one is the solution for the system. And using the formula, e to the at is xt x0 inverse. We have xt, we don't have x0 inverse, so we have to find it, right? So what is x0? This is a matrix. When we, instead of t, we just write 0. So we have 0, minus 2, 0, 0, 1, 2, and 1, 0, 1. So we need to look at this matrix and we need to find its inverse. Let me just write the value of the inverse. You can check that this is indeed, an inverse of this matrix. This is minus 1 over 4, minus 1 over 2, 1, minus 1 over 2, 0, 0, 1 over 4, 1 over 2, 0. So as soon as we get this one, the e to the at will be x of t multiplied by x0 inverse, and x of t is 0 minus 2 e to the t, 0, 0 e to the t, 2 e to the 3t, e to the t, t e to the t, e to the 3t, and we multiply these two matrices, minus 1 over 4, minus 1 over 2, 1, 1 over 2, 0, 0, 1 over 4, 1 over 2, 0. So, and we get this times this. So the first row times the first column here, we get just e to the t. This times this, we get 0. This times the third column, also 0. This times the first column, we get minus 1 over 2 e to the t plus 1 over 2 e to the 3t. This one times this one, we get just e to the 3t, and this row times the last one, we get just 0. And finally, for the last row, we have to multiply last row here by the columns. So this will be minus 1 over 4 e to the t, minus 1 over 2 t e to the t, plus 1 over 4 e to the 3t. Multiply this by this, we get minus 1 over 2 e to the t, plus 1 over 2 e to the 3t, and for the last term we have just e to the t here. So this is the answer for this particular problem. This is e to the at.